let's just consider the details of the process. We want to maximize some function on some function of three variables on a surface within those three dimensions. For example, a temperature function on a sphere, ellipsoid, whatever surface. The condition is that the gradient of t has to be parallel to the normal vector to the surface. So the normal vectors for the surface, delta t, is related to our temperature function. And it's not delta t, it's del t. Okay, so del t is nothing but txi plus tyj plus tzk has to be parallel to the normal vector, which is just del f equals fxi plus fyj plus fzk. Now, how are two vectors parallel? Well, they're parallel if their dot product is equal to the product of their magnitudes, but a more useful criterion for this purpose is just that two vectors are parallel if and only if one is a multiple of the other. Okay, now I've missed something here I probably should have labeled. This is del t equals this, parallel to del f equals this. Now, vectors are parallel if and only if one is a multiple of the other. So del t is parallel to del f if and only if there exists a constant, and we could call this constant anything we want to, since Lagrange was the one who either came up with or somehow communicated something somebody else had come up with, and you want to think that Lagrange, being Lagrange, actually came up with it himself, I would expect. I don't know the history of that, so I can't say. But if del t is parallel to del f, if and only if there exists a constant, okay, that constant can have any name. Lagrange is associated with this method, one way or another. So we're going to use the Greek letter lambda, which kind of corresponds to our L, sort of in deference to Lagrange. So we're going to call this constant lambda, and that's going to be a lambda such that del t equals lambda times del f. Our condition that the two vectors be parallel then comes down to txi plus tyj plus tzk equals lambda times fxi plus fyj plus fzk. Now, two vectors are equal if and only if if their three components are respectively equal. So that this equality is going to hold only if and only if tx equals lambda fx, ty equals lambda fy, and tz equals lambda fz. Now let me comment again on the economical way to remember this method. Now, what's the most economical way is going to depend as much on how well you remember formulas that you see as opposed to geometrical situations. Most people, I believe, will have an easier time remembering that del T is supposed to be parallel to del F, and that happens if and only if there exists such a constant, than to remember these three equations and the fourth equation, which is f of x, y, z equals 0. In practical terms, of course, most people are just going to look it up every time they need to use it and not even think about why it's so. However, if you have to look it up every time you use it, and if you don't understand the geometry, it's probably going to be more difficult to do creative things with it if you don't really understand what the formula is telling you. Again, in my opinion, for most people, easier to really remember a principle. My comment that I've made a number of times in my life is that education seems to be more about memorizing 10,000 rules when you can memorize a handful of principles, when you can learn a handful of principles. Why teach a few principles when you can teach 10,000 rules? Well, I think the answer to that is obvious and might be illustrated by this situation. But once more, that depends on learning styles and so forth. So there's no reason to feel badly if you'd rather remember these formulas than remember the picture. In any case, these three formulas embody the condition that del T be parallel to del F, and the fourth equation is f of x, y, z equals 0. Now, tx, ty, tz, fx, fy, and fz are all simply expressions in terms of x, y, z. So these are just equations in x, y, z, and lambda. This is an equation that's just in x, y, z. Lambda doesn't even appear. But the point is, now we have four equations in the four unknowns, x, y, z, lambda. If we can solve these four equations, then we get the coordinates x, y, and z of a point where the function can have a relative maximum or a relative minimum. We also get the multiplier lambda, which can have a significant interpretation.